All right, boys. Hope you're doing well. Hope you're safe, healthy, and getting along with your family and appreciating what is appropriate to be appreciated now. So, for this particular video, I want to show you a use of a differential equation, and B, how we get around a little tricky algebraic manipulation with logs and exponents. So, here we go. This we're going to derive what you guys probably remember or refer to as the Pert model, right? Recall that that's the, if it's a function, it has lots of different faces and looks, but that's the continuous and exponential growth and decay model, right? Carbon dating, for example, uses that, right? Continuous growth, decay, exponential model. So we're going to derive that now using a differential equation. So we start with the derivative of some function y with respect to t is equal to some real number value, we call that a coefficient k, times the function itself, y. So what function has a rate of change, a derivative with respect to time, that's equal to a multiple k of itself times y? Right? Recall that in these differential equations, at least for now, we're solving for y, and these differential equations too, hopefully, are separable. Okay, and of the two steps for separable differential equations, at least of the basic variety, we're going to first separate the variables. So step one, I want to separate. Okay, and well, what's to separate? Well, I want to certainly put the y with the differential y, and I want to move the dt over to the other side too. So I'm just going to multiply both sides by dt, and then I'm going to divide both sides by y. So what I'm left with is this, dy over divide by y equals k times dt. Okay, so I just separated. I put the y with the differential y on the left, and I put k, the coefficient, some real number value with the differential t on the right. Okay, so k can be 3 or 8 or 22 or pi, it doesn't matter. Okay, now the next step I want to work through is, okay, I have a differential equation that's now separated. Okay, I now want to integrate, right? So I want to work backwards. I know what the derivative looks like, and I want to know what y is, a solution that has a derivative that's a multiple of itself, right? So I just integrate now both sides. Here's my little indefinite interval sign. And then on the left, recall I'm integrating with respect to y. That's what that dy means, right? And the antiderivative, if you recall, of 1 over y with respect to y is ln y. Right? And I'm going to put the y in absolute value bars, recognizing that you can't take the log, natural or otherwise, of any 0 or negative value. Okay? And on the right, I'm going to integrate some value k. It could be a 3, it could be 7, it could be negative 43.2 with respect to t, though, right? I'm integrating the right side with respect to t. Therefore, the antiderivative 3 or 47 or k with respect to t is k times t, right? And now those of you, Austin and others, saying, well, wait a minute, you forgot your constant of integration. Now, that's a little tricky here. We have some constant of integration on the left, another one on the right. It's overall, you can combine them to be one general constant, and I'm just going to call that constant c, okay, on the right. All right, so far I've solved, at least for now, at least found the general solution for my original differential equation. dy dt equals some multiple of itself, some k times y being this function we're looking for. Okay, now I got the other piece I want to show you is how we deal with this. So forget about the calculus now, right? I want my solution to be y in terms of t, right? That's would be a lot cleaner, right? So what I'm going to do right now is kind of refer back to some logarithmic rules. Recall that if log base b of m is n, I can just rewrite that as its equivalent exponential, right? Okay, that's called exponentiating. So I'm going to do that now, right? Remember, the base of the natural log is e, Euler's constant, it's about 2.718-ish. And so I'm just going to exponentiate this logarithmic equation, right? So I end up with y. I'm going to drop the absolute value bars. I'm going to be a little lazy. Equals e, the base of the natural log, to the kt plus c. Right? That's its equivalent exponential look. Okay. And now here's a little trick, right? There's another rule of powers. It said, all right, if you have some base to some power times another base, excuse me, the same base to a different power, you end up with that same base b to the add the powers, right? So I'm going to work that same property of exponents backwards. And I'm going to rewrite e to the kt plus c, right? It's a sum. There's a sum here. So I'm just going to work that backwards and call it e to the kt times e to the c. Okay? And now here's a little trick, and we oftentimes do this, and I think I showed this in the other live class. Check that video out if you want to. But since c is some constant, some unknown, then e to the c is some constant, some unknown. So what we oftentimes do here, because it's a little cleaner, is I replace e to some constant with some other general constant. I'm just going to call that c naught, or some other not c value, right? So I don't really know what c is. This technically is still the general solution because it has that constant of integration in it, right, of the original differential equation. dy dt equals k times y, right? But really I want to make it look a little cleaner. So that c, that general solution, still has that c in it. E to the c is some constant, so I just call e to the c some other constant, c naught, right? You can call it whatever I want, really. Okay, and then I just rewrite the order. So I put the c naught in front, and then e to the kt. Okay, and this is a general solution for that differential equation that we started with, right? dy dt equals ky. The derivative with respect to t of what function y equals k, some coefficient, some multiple of itself, right? We're solving for y. We just got our solution y. And what do you know? It's the same as a Pert model, right? Just different letters, right? So that's how we derive this continuous growth decay model. It's a really nice way of doing so. And it uses, of course, a differential equation. And then, oops,